a kind of general setup of how some unitary operation can be broken down into elementary quantum gates. Now comes the question of counting the effort required to implement that particular circuit, which is already reduced to some set of operations. So the first part was to just count the number of factors, but as I mentioned in the previous class, we have to perform an analysis of the error bounds because everything is probabilistic and things will not be perfect in a real life implementation. So you want to implement some operation u, you will implement some close approximation to it, u tilde, and then the question is how large is the error, because we want to keep the error bounded. If the error goes out of the control, the calculation is of no use. So I defined this structure last time. I will repeat it. So there is some general operator u which we want to implement, which is product of some sequential factors which are all individual logic gates, and then we have the approximate version of it, which is just defined by similar structure, but I put a tilde on the u saying that this one is different than this one by some bound. So then the next step was to define what you mean by the error, and that was labeled as I put an index t for some particular time is equal to uj tilde minus, no, not j, I have to write t everywhere. Where phi t minus 1 stood for the exact solution at time t minus 1, then this is the difference between the two operators and it produces some error. If you just use ut acting on phi t minus 1, it will generate phi t, which is the exact solution. And then just by compounding all these results together, we had a simple constraint that this is the approximate solution, this is the exact solution, and you take a magnitude of it, and that is bounded by the error at the individual steps. This was nothing but the application of a triangle inequality. You have some error occurring at every individual steps. So the total error is bounded by the sum of all the errors. When all these error vectors are parallel, you get the maximum value. If they are in different directions, there will be some cancellation and the result will be smaller. So this is what I mentioned last time. We have to go one step further because the error which we want is not on the vector, which is fine for discussing the Hilbert space, but what we measure is the error on the probability of whatever observation you make. And those probabilities are given by the usual rule of some set of orthogonal vectors. They are determined by what you choose to measure, and if you get an observation of A, the probability is given by this, and this is just a definition of orthogonal measurement. And what we want is a bound on this quantity which is the difference between the approximate probability minus the exact probability, and summed over all possibilities, the largest value that it can take. Okay, I put the absolute value sign and summed over all possible results of the measurement. What is this object? Well, it's not too difficult to guess what it would be. That if there is a error epsilon, then the error on this thing will be square of it, so 1 plus epsilon square will become 1 plus 2 epsilon, so that should be about twice the size of the error. But we can do it more rigorously by just plugging in the explicit form of this quantity. It is one quantity square minus another quantity square, so factorization is not complicated. Let me just write it the absolute value for all these things. So this is one factor, and the other factor will be the same with a minus sign. Okay. So now this is just a simple factorization of x square minus y square, giving you x plus y times x minus y. Now this can be seen as a dot product of these two components. This summation over A is just a sum over all the components which are involved in the dot product. So I can use the so-called Cauchy-Schwarz inequality, which says that what is A dot B? It is always smaller than mod of A multiplied by mod of B. Okay, so you can write this thing as this is vector, so its norm appears. Too many of these signs, or whatever it is. So these double lines are for the norm. So this is the Cauchy-Schwarz.
Equal to sign or equal to sign?
Huh? It's an inequality. Now you can work it out further, and this has a trivial bound. This is some component along some direction, but the vectors are all normalized, so whatever the component it is does not exceed 1. So I will just take 1 plus 1 is equal to 2. What is this particular object? This is now what is known as a triangle inequality. This is the difference of the two magnitudes, and that is by the triangle inequality less than the actual vectors. Difference of that. This is actually the length. So the triangle inequality has two parts. You add two vectors. They are less than the sum of the two and greater than the difference of the two. But all the sum and the difference are taken with the absolute values of whatever the lengths are. So this becomes this, and that is exactly what we wanted, that I can now take this A outside, and it becomes phi tilde t minus phi t, the structure which is sitting over here, and that is basically the final result. So this is less than or equal to 2 times this particular quantity which we calculated. Okay, so now I wrote down one result. What is this particular length of the vector? It will be given as a difference of these two matrices, which can be characterized in terms of their eigenvalues. So that result is that if you have we can factor out one unitary matrix, so it's I, or we'll just write down U T tilde U T daggers unitary matrix, so the eigenvalues are just going to be some phases, and you want to put a bound on it, and the largest eigenvalue I just parameterized I think I called it by label theta. With whatever the index is. So then the norm of this object, this has a length 1 by construction, and this is the difference between I e raised to I theta minus 1, and that is given a trivial bound. That what we end up by doing all this exercise is let some epsilon is equal to maximum value over all the t of theta t, and then this object becomes sum over all the time steps, which is given by this index t. So I have to give initial state is final state is phi t, some labels. Initial state is phi 0, etc. And then you get this result, the bound, which is our measure of how much error occurs. P tilde A minus PA is less than or equal to 2 times T times epsilon. The 2 came from here, and the T came from all the summation over all the intermediate steps, and epsilon was the error in a single vector which came from this particular definition, and it's maximized over whatever the largest value is occurring over the whole game. So this is explicit bound on the error. And what does it mean? Well, I can write it down explicitly that if exact algorithm succeeds with probability 1/2 plus delta. This is what we labeled in the complexity analysis, probably has to be little bit larger than half. Then you can take care of everything. Then the approximate algorithm will also succeed with probability greater than half when the error which can occur is less than delta.
If algorithm is exact, how it can fail?
Why there is a probability? If you don't mind on the ideal algorithm, which I mean by applying the operators U, the approximate algorithm is one which applies operators U tilde. No matter whatever it is, finally you will measure some probability of some measurement basis, and they will be given by expressions like this.
Here, what is the meaning of success of algorithm? It's I not get the desired answer.
We had broken down all the problems into decision problems. Yes or no. Success means that I get the correct answer. Failure means I get the wrong answer. There are only two possibilities of answer, yes or no.
So how ideal algorithm, why this will fail?
Because the situation is probabilistic. Probabilistic algorithms do not succeed with 100% rate. They succeed with some rate, and the point was that I don't want it to be a random toss, because if it was just half, I don't have to do the work at all. I will just toss a coin and go ahead with it. I want the probability to be larger than half. So by multiple trials, the probability can be increased to closer than 1. That is the paradigm of this bounded error calculations in general. So this is a criterion which we arrived at, that the algorithm will succeed with probability larger than half, provided this condition is satisfied. And we choose some delta to some finite value, and then it tells me epsilon is a measure of how different are the approximate and the ideal unitary transformations are, and T is the number of objects, how many of these operators are applied. I have not given you criterion for T so far. There can be too many of them, and then the whole thing will not work. If the T is not polynomial, then the effort required to bring this down will be super polynomial, and that will not be worth effort.
When we say largest one is e raised to theta t, we mean the value of theta or
At largest eigenvalue.
but everything has got magnitude of the so what is the all the eigenvalues have got magnitude of the
This operator will have lots of eigenvalues. All of them are of phase form. Among these lots of eigenvalues, the largest one I am labeling as this.
what is the largest in a phase? Like the phase is the largest? Maximum phase?
Largest phase I want, if not the eigenvalue. Maximum difference from identity. So I should write, eigenphase if you want. Change the words a little bit. It's the largest eigenphase gives, because to take the largest eigenphase among all of these, this is the maximum departure from 1. Okay. So this is one part of the story. We did a general analysis. We have not assumed any particular property of what the algorithm is, etc. But we found this particular bound when we have an approximate result. We need to emphasize one particular point, that the dependence is linear in time. And the reason is that we assumed certain property. And so what is it to be compared with it what happens in a classical case. So you can go through all these numbers in some particular situation, but the overall factors turn out to be something like this, that there is a one with its ideal case, there is an epsilon, and the approximate will be 1 plus epsilon first step. There are so many steps, it goes into the exponent, and this was the case where there was no error, so I have to subtract out to get the difference. And this object behaves like e raised to epsilon times t. Okay. And if epsilon is some number, it can be small, even at say 1% or something like that, the t is sitting in the exponent. So this is basically it's an exponential growth. So in the classical algorithm, if you have multiple steps and each step you make an error epsilon, this is what you'll end up with. And we have somehow bypassed it by our assumption, and that assumption is that the approximate operation is u tilde. It is not the same as u, but it is still unitary. Okay, that is the crucial point. In the classical algorithm, the error will be dealt as just a real number, and this is what you will end up with. And here, because the object is a unitary, essentially you get instead of 1 plus epsilon e raised to I epsilon. This is the original value which is perturbed. Here when you perturbed, you change from 1 to e raised to I epsilon, and the point is this does not grow. It's a number of one magnitude. You can take a large power, still it is number of magnitude 1. Here if you had a real number sitting over in this mirror, it is going to grow exponentially, because 1 plus epsilon I can write approximately as e raised to epsilon. And that's where this behavior came from. But here the number is just a phase, and this therefore grows as, well, order epsilon times t. So that is all that can happen. How far you can go, the largest value is 1, but if you want to expand it in a series, it will be e raised to I epsilon t. You can expand it out 1 plus I epsilon t, etc., and you'll end up with this behavior, and that is what we are seeing here. So the error is completely different because the error occurs in the phase and it does not occur in the magnitude. That is the assumption which we have made. So the error grows only linearly with not exponentially. So this is a crucial difference, and that is what helps in looking at the behavior of the algorithms. Okay. So now I want to put this thing in a sort of complexity counting. Of a general algorithm, we'll see the constraint on the type of algorithm which are going to be useful coming out of all those things, because complexity analysis I want to keep polynomial. I don't want to grow it exponentially in terms of the operations, and all these things are going to be ingredients of that situation in some form or the other. So what we have is a kind of general evolution is given by the some initial state operated by this sequence in some form or the other going to some final state. That is a quantum version of input, some logic operation going to output. So this is what happens in the algorithm, and you want to count the complexity of this thing. What can be written, and there is a standard way of decomposing this thing into individual steps, which goes like this, that you introduce intermediate states after each operation of a unitary factor and sum over all the intermediate state, which is the completeness relation. So I can write this is f ut times xt ut minus 1 etc. going all the way to x1 u 0, and then there will be x0. So whichever way I was ordering it, the index is these two have the same index. Okay. Or actually, let me write 1. So because I was using a convention. And the first one is just some I. That is what I wrote over here. So I started with I. I acted on U1, introduced a complete set of states. Then from x2, I will operate by another factor of u. It will go to x3, etc. And to maintain the completeness of the relation, all these intermediate states are summed over. So that is satisfied by the identity that this cat xt times bra xt summed over all the possibilities of x is equal to I. That is the completeness relation in the vector space. So I have a representation like this, and for those who have encountered this structure before, it is a so-called path integral representation where you start with something, there is a one path made up of certain intermediate state and summed over all possibilities, and it gives the final result. If you have not seen this label before, don't worry about it. It is nothing but the completeness relation in the vector space. And so how many terms are there in this summation? So that I now to count that I work with n qubits. So each uj is a 2 raised to n times 2 raised to n matrix. And whatever it is, each x has 2 raised to n components. So how many terms are there. So this each one has 2 raised to n, and they have summed over all the intermediate steps starting from 1 to t. The final is step t, and you count how many of them are occurring at t minus 1 intermediate steps you have to put inside. Those are the values of all this x. Remember the convention, the way I have put it, it starts with 2 and ends with t, so the number inside is t minus 1. 1 doesn't matter, but this is just for the completeness. So now I want to say that I want to calculate this thing to some accuracy. And that is equal to sum over so many terms. So what is the accuracy that will be needed for individual terms? So final accuracy will be maintained whatever I want to label it, some parameter you can put epsilon or something like that. I'm not writing it down. When individual terms have to be evaluated to much higher accuracy. Because I'm summing up so many different terms, every term will have some error. If I add up many terms, the error will be the individual term error multiplied the number of the terms. So I have a huge number of terms buried inside it. So evaluated to m bit accuracy with m greater than the accuracy. If you have m bit, accuracy will be 2 to the power minus m. Okay, so what you end up with is this constraint that m is greater than n times t minus 1. So whatever the initial accuracy you want, you have to add so many extra bits of accuracy to the individual terms before you add them. Because individual terms will have extra accuracy of 2 raised to minus m, that are the number of bits you need to add, and 2 raised to minus m multiplied by this particular factor will give you the original whatever accuracy you wanted. The point is you need so many extra bits. That is essentially the point in the calculation. So now the space requirements are determined. One is this n qubits required some space. That was the input to the algorithm, and m bits for extra accuracy. Whatever the original gave some answer, I am calculating in term by term. I have to calculate the same result to a higher accuracy before I add them up. The point is that this number is also linear in time. I have not specified what time is so far. So, what is the time requirement? Well, it is the two quantity which I calculated, that error and this m are linear. That's all I have, and this is the kind of general analysis that yes, I will have approximate results, I will have some calculation done in some sequence of operations, how many terms are there in the sequence of operation, where that is specified by this t. But the resources are all now written as a function of the number of steps which are there in the algorithm, and the problem which we want to solve is efficient provided these resources are polynomial. Okay, so this is the class of problem which I had introduced earlier. BQP, it's a bounded error, quantum polynomial has t which is some polynomial function of the input size. And all this analysis, what it told you that yes, you can take care of bounded error, you can take care of the extra precision, and all those things will also remain polynomial in T, provided T is polynomial in N. It's equally linear, it's not that, but not a higher degree polynomial, but if T is polynomial in N, then everything will become polynomial in N. That is essentially the point. And these problems, therefore, are efficiently solvable. Why is this an improvement? The improvement is buried inside various things. One of the label which saw this contradiction between classical and quantum, something which turned from exponential to polynomial over there. So there will be problems where the classical error has to be much more strictly governed, but in the quantum one, the error will be much better controlled. This part summing up of various terms actually doesn't give any obvious connection between quantum and classical. You can write it either way. So the statement is that it is possible for BQP class to solve problems So the quantum resources of BQP are explicitly polynomial, but the corresponding classical resources may be exponential. The difference buried inside, in some sense, how fast the errors grows, and these problems, which are classically hard, are labeled by the corresponding classical label, which is given by the acronym BPP, which is the same thing, bounded error probabilistic polynomial. And the probabilistic polynomial will go through this analysis, essential difference coming between how fast the errors grow in a probabilistic algorithm. And of course, the what you call bounded error algorithms are much more general than the deterministic algorithms. So all the other definitions are contained inside here. But I mentioned this earlier that this hierarchy is this. If you have a deterministic algorithm, the bounded one is much more general, and this one is even still more general because it saves something else. But relation of BQP and NP, which is often quoted classical class, non-deterministic polynomial, it is still unknown. This much you can say, and the whole exercise of inventing quantum algorithms are try to find some BQP algorithm which is not inside this bounded error polynomial class. So that means it is beyond this. It may be in the class NP, or it may be something else, we don't know. But it will be a hard problem because it is not in BPP. And some examples of that we will encounter, but this problem is still open whether BQP is included in NP or it has some only finite intersection with NP, or there could be something in BQP which is not in NP, we don't know. Okay. So this is essentially the crux of the analysis of what are the kind of problems that we want to study. This is explicit counting of everything that we are going to use, and now comes the stage of giving simple examples where you can see the difference between classical and the quantum version. So now all the introductory part of quantum mechanics and complexity analysis is over. We are roughly halfway into the course, and now we are going to study various algorithms one by one.
So the BPP problems are the classical or we can say BQP are the quantum counterpart of BPP.
Yes.
So, sir, does BPP also give some relations for T, sir? T should be the polynomial in N or something like that.
They are all polynomial. P, whenever it appears, is polynomial in N. All of them are polynomial in N.
T is a polynomial in N.
Yeah. So the N is already the description of the space size. So when I say polynomial N, it refers to the time. How many time steps it will reach the final result. The input is a polynomial already in the number of bits or number of qubits or whatever they may be.
So, how then taking that if it is for the classical model,
Yeah.
it is exponential.
Yes.
So how will we come to know which is a hard problem and which is a easier problem?
Yeah, so you can calculate now what is the T you will need for a fixed epsilon. And that T will be exponential in terms of whatever bound you put in epsilon. And instead of being linear, you will end up with exponential in T. And that's how this time requirement goes up. What has happened here is the space requirement is polynomial. So one can say that this is there's another class of problems. So whenever this space requirement becomes polynomial, the class called p-space. And p-space is a class which is bigger than all of them. Okay, it includes everything. And you remain inside this fixed space requirement, and then you look at the behavior of time.
Sir, I'm just asking one thing. Is there any limit of T which will tell us that below this the problem will be easy and above this T the problem will be hard?
No, the behavior or the classification is always done in the asymptotic limit, T large. Or large T, whether it is polynomial or whether it is exponential. This does not say anything about what will happen with finite T. Okay. So we'll start with a very simple algorithm. It's nothing to do with the asymptotic analysis because it's finite in every sense. There is no large number of bits involved in any particular case, but it shows that with quantum setting you can do something better. Okay. And this was actually the hypothetical problem cooked up by Deutsch. and it's phrased like this, that there is some unknown function f which is just 1 bit. Input is 1 bit, output is 1 bit. And the task is to find if f is one to one or two to one. There is no other option for this 1 bit function. It has to be either of these two choices. And well, the classical result is that the only way you can tell is evaluate both f0 and f1. If they are different, the function is 1 to 1. If they are the same, the function is 2 to 1. There's nothing else you can do. Function is left unspecified, so this is sometimes is referred to as a relativized problem. So this is a label which is used for with f as some kind of black box. You can ask, I evaluate f of 0, and the black box will give you the result. How it is calculated, none of your concern. So this is the classical thing. You have to evaluate the function twice. And Deutsch wrote down an answer where the classical thing is improved by saying that in quantum logic you have to calculate f only once. And there is a simple circuit which does that particular job. So let me just write that circuit first, and then we will evaluate all the operations. So the circuit goes like, there is there are two qubits. One is initialized to 0, the other is initialized to 1. Then we apply this Hadamard operator, which I had written down earlier. It can be written in many different ways. And one way of writing this object is acting on the two indices with a phase, where the only one which is non-trivial is where both the indices are equal to 1. Then it becomes -1. This is just the ordinary product of x and y. Otherwise, all the other three values will give you +1. And this is a reminiscent of something which will be much more heavily used. So let me write down that one as well. That this is the so-called one-bit Fourier transform. In a general Fourier transform, you will have e raised to I xy. And this is not e raised to I, this is -1. That is restricted because you are using only one bit. But that is a side remark. So now let us look at what this object does. So I have to specify what is this operation UF, and the definition I had used earlier was to let me put some general state. The reversible execution of this operator, it's some state I, whatever it does, it is just binary addition of this value f to it. F has only two possibilities, it's a one-bit function, so it's like a control not kind of thing, and you can add this particular result. The peculiarity or whatever happens by choosing some particular state. So this h acting on 1 is 1 by root 2, 0, -1.
Here is x here.
Hmm?
What is x? Is above 0 input or 1 input?
Whatever is the value you want to add, it's coming from outside from the black box, and you just added it to the whatever value existed in the result. Because it's going to act like this control. So I is the value which is here, x is the one which is coming from outside. Some notation, but you have to kind of digest it. That's all I can say. And if you want to write it more generally, this is what the Fourier transform will make it more explicit. Which is I wrote down here. It is the same thing, but now it is written in a language where the Fourier transform is much better explained, that you have some function here, multiply a particular phase. This is a particular case of this particular result. So now ask what is going to happen when this f coming from outside gets added to this particular state. Okay, so I should want to write it as a two arguments. It is probably better because I'm using a control U notation. So let me also write it in the similar language, that there is a x here, this I wrote as I, and it was taking to x and I plus f of x. This is this controlled operation. Just writing the 2 bits. The x is coming from the control, and I is whatever the value is sitting in this particular register. And this is a sort of definition. What do you mean by control? That it gets added to whatever the result is sitting over here. X decides whether you add 0 or whether you add 1. And then UF acting on this state. Well, I have to write two components to it. So it's UF acting on X, and then this, what will it become? Well, you are going to add whatever the value is, the value of F to it. So this is going to remain what it is, and then it's a 1 by root 2 minus 1 raised to let me follow the same notation to avoid confusion. Okay, so here I have used a particular property that fx, whatever it is either 0 or 1. So, yeah.
You are considering it is not in a superposition.
Superposition is all over the place. The linear combination of vectors that is already created by this so-called Hadamard operation of Fourier transform or whatever it is. So why I am able to write it like this is because the fx has only 2 answers. It's either 0 or it's 1. It's a 1-to-1 function, 1 bit function. So if I now look at this, if fx is equal to 0, I add 0 to both of them, the state remains itself. So I will rewrite it as minus 1 raised to 0, which is fine. And the peculiarity is if fx equal to 1, I add 1 to both of these quantities, it will become 1 minus 0, which is equivalent to factoring out a minus sign and writing the same combination. So this operation, what it essentially did was take out the fx which was in the additive form inside the gate and bring it outside as a phase. And this is a standard way of including functions in quantum algorithm. You don't want to have them as an addition to the value. you want to put them in the phase. The phase is something which is very useful in lots of manipulation. You are going to do essentially interference by having superposition of states. So that is where all the tricks are there. You create a superposition and you have phases which will interfere, and that will give you the interesting results. So now let us, these are all the definitions of what happens and what are the various operations. Now we can evaluate the result of this particular circuit. So this algorithm. What is the first step? The first initial state is using these two operations, so it will become half. The first bit is 0 plus 1 and the second bit is 0 minus 1. That is just a result of the Hadamard operator acting on 0, and this is 1. Now I apply UF. Okay. So I will just write down everything by brute force. I have the result already here, but I am putting now the values for x. It can be either 0 or it can be just equal to 1. So there are two terms. If x is equal to 0, I will have 0 and minus 1 raised to f of 0. And if it's 1, then it will minus 1 raised to f of 1. This one doesn't change. So the second factor is still 0 minus 1. And then I'm not going to do anything to the second factor. It remains whatever it is. I'm going to apply another this Hadamard operator on the first bit. Okay, so now it is h times identity. And what will happen? 0 will become 0 plus 1 by root 2. 1 will become 0 minus 1 by root 2. So it's 1 more root 2. Okay. And I will write the quotient combined together. Nothing happened over here. So 0 produced two terms. It is 0 plus 1 and the factor is minus 1 raised to f of 0. And 1 produced two terms, which is 0 and minus sign 1, and it had a factor of minus 1 raised to f of 1. And that is the stage where I measure. Okay.
So is it the UF acting on the second qubit, the one is getting converted to 0 minus 1?
Yeah.
Instead of acting on the 0 plus 1. Like the control qubit is 0 plus 1, like after the Hadamard.
Yeah.
And the second qubit is 0 minus 1.
Yes.
So UF is acting on 0 minus 1 or 0 plus 1? It's acting on 0.
It's on the tensor product. It's acting on the both qubits simultaneously. It has, this is a control U operation, and what is happening is defined in here. It adds the function value, whatever it is, to the second register, but because it is 0 minus 1, the additional value goes up into the phase. And so now you measure And if f0 is equal to f of 1, there are only two possibilities. This will vanish and you will get the result 0. And if they are not equal, then this stuff will vanish. Remember, not equal means one of them is 0 and other one is equal to 1. This will vanish and this will survive. So you have two measurement results. They tell you that the f0 and f1, they are either equal or unequal. And that was the problem I started out to solve, whether the function is 1 to 1 or 2 to 1. So this is and so what happened in the algorithm is I solved the problem by evaluating the function only once. That is all the difference is. Here I had to evaluate it twice. And how did it work? Because I used a superposition of state, and that allowed me to do an interference between the two components, and it was arranged so that I will get the desired result with less number of function evaluation. Less is only a factor of 2, but that is all that is needed. So superposition and interference are used to solve problem with only one
One question here.
Hmm?
One question. Here, qubit X is working as a control qubit,
Yeah.
and it looks like below one. Below, it is affected from below one, so it got changed, and after that it will either give me 0 or 1. If it would not get affected, then it would give me only 0.
Yeah, so you are arranging. This is the design of the algorithm. Why you are using this and not that, that is essentially the design. You could have used different inputs over here and then it would not have worked. That's not the question.
We are ultimately giving input 0
Yeah,
input, and then it will convert it to plus basis.
yeah.
Plus, and then if it is not get affected with this thing, because it is control.
Yeah, we defined all those operations systematically with all the algorithms of a reversible logic. And
Then again we apply Adam add-on plus should give me only 0. No.
Because it's like a control. So it's
It is 2 qubit operation, so that it is affecting the above one also.
it's not like it's the interference.
Okay. It is affecting the first also.
this is a UF I have written is a, well, probably or to be more explicit, this is not just UF if you want, this is a control UF.
Okay, even
Sure.
if we consider control U, So in matrix form, it is possible that first qubit is affected in controlled U. Controlled U gate, first qubit can also be affected.
The phases of the first
Okay.
the phases were not there in the being got seen. Since the phases are affected, that changes.
So only phases are affected.
So this kind of looked artificial in terms of a problem, and what you gained is, well, you have to use only one function evaluation, that is fine. But it was soon converted to something which is more dramatic, though it required another convention, but the reason is quite straightforward to see, and it generalized this function very simple manner. So this f goes from n bit to 1 bit instead of being 1 bit to 1 bit. And well, then the question is, I have to redefine this meaning of 1 to 1 and 2 to 1, and that you are given that f is either constant or balanced. Constant means all the 2 raised to n values are mapped into just one value, and balanced means half of them are mapped to 0, the other half are mapped to 1. Okay. It's a different, so and your job is now to find which of these two possibilities are correct. It is still a decision problem, yes or no. Now again, the classical version will evaluate f at various points and keep on checking whether the values come out to be same or at some stage it is different. So if it keeps on coming out same, then it's constant, but at some stage the value flips, then you know that it is in the other class. And the worst case scenario is that you don't have any idea about which order I should look at all the i's. So maybe after I have gone through all the half of them, the next one has a different result, and the worst case scenario can be large. So worst case needs 2 raised to n by 2 plus 1 evaluations. You have to cross this half somehow or the other, and then you will only have a guaranteed answer. And the quantum algorithm is the same, except that I will Yeah, this is probably half of them, so it's n minus 1. I wrote it wrong. Okay. Half of 2 raised to n, whatever it is. So, all that is done in this algorithm is, here you had only 1 bit. Now the function is from n bits to 1 bit. So you replace this object, instead of 0, it will be 0 to the power n. And so this h, whatever it is, it will be also become h to the power n, where n is the number of qubits, and it just applied to each one of them one by one. This part doesn't change. It's a control, and it will produce whatever this x is minus 1 raised to f of x. It doesn't matter because this definition was independent of the value of x. It only depended on whether the output f of x is either 0 or 1. So the remaining part of the algorithms don't change. What changes is what you mean by this object. So, and what is that object, which is actually just this? I have to write a generalization of this relation to n bits. So it is a summation over n dimensional space, and then root 2 becomes 2 raised to n by 2, and it is going to operate individually on each bit. It's completely factorized. So what I will get is this particular factor for every bit. It's completely simple enough to denote by the factor with every bit, say x1, y1 plus x2, y2 plus x3, y3. I can write it as a dot product. That's all that happens. The rest of the stuff goes through, and I can write it again in terms of this dot product notation that doesn't matter too much. So the algorithm gives with 1 over 2 raised to n, this got squared, and then there is a summation over x and y, which came from this x summation came as a generalization of this superposition, because we have seen that h raised to n acting on a 0, well, this is actually acting on a general state, so I should 0, it becomes kind of spatial. This is it's a special case which, because it's had both n x inside it. This I have written before as well, so you could have put x equal to 0, then all these phase factors vanish, and it is just a summation over all the states with equal weight. So that is the factor which comes from here. When you now go to a more complicated situation, that it can be any other state, and you apply this control operation, what you end up with is minus 1 raised to f x minus 1 raised to x dotted with y acting on y. That is all the generalization. This minus 1 raised to f actually came from this particular evaluation of the function over a very specific state which was 0 or minus 1. These factors came with every combination. That is what appeared over here, and the input which was feeding into it, it could have been any of the complicated states, and that produces this other factor. I am not performing the measurement yet. So you started with this uniform superposition and the other one 0 minus 1. Acted by UF, it produced this minus 1 raised to f of x because that was its job. Then whatever the state was, I acted on by another h to the power n. And that action on h raised to n on x arbitrary state produced this minus 1 raised to x dot y. And that is all there is. There is nothing more in the algorithm. Now we have to ask what happens when you measure. Okay, my time is up. I'll just write down the result of the measurement. What happens in this expression? That when the function is constant, this factor is absent. And then the second factor remains. And what is the summation over minus 1 x dotted with y when you sum over all possible values of x? That if any bit of y is non-zero, then there will be two terms, one corresponding to x equal to 0 and x equal to 1, which will come with opposite signs. And that will cancel out. So, only the term which will survive this summation is y equal to 0. Actually, this is a discrete version of a representation delta function. That you can write it as a more generally yeah, it's not necessary To do that, let me just complete this. And when fx is balanced, something else happens, that it's balanced means half of them will have value +1 and other half has value -1. And then when is this factor absent? If y is equal to 0, this factor is not there. And then half of them are +1, the other half of -1. It doesn't appear at all. So that solves the problem. You measure the output. If it is 0, function is constant. If it is non-zero, the function is balanced. You are not worried about lots of possibility which are there. Actually, 0 is ruled out, that is all you count. Otherwise, y has n bits or 2 raised to n possible values. You are not going into that much detail. So the job is done, so only task complete. So here is something which is much more dramatic, because the classical version, the guaranteed answer had a exponential number of evolution. The quantum version did the job with only one trial. Why it happened is all buried inside this superposition and interference. You have 2 raised to n terms, you arrange them, somehow these things cancelled, some things are added, whatever it is, but it added in a very clever manner, and that is the consequence. So yeah, I will stop at there. If you don't understand this, ask me question next time. Because algebra is not complicated, but how the superposition and interference are getting involved, that is the important part of the exercise.